So yes, good morning. I suppose we should just begin where we left off with the spectral element method, which is the last topic of this course. So I briefly started with the equations that went a bit too fast, so I'll just repeat them and in a slightly different manner. So now I will just drop the spatial and temporal dependencies and then just write them out later instead of directly in the equation. So you would have the density dependent on space, displacement dependent on space and time, partial derivative of the sigma xx stresses, y, y, and some force f of x. First one, let me have this a bit smaller. I'm going to use y, double dots, dy, sigma yy, x, sigma xy plus a force term. So that's for the displacements and the stresses, sigmas. They are sigma xx. So this lambda and mu, those are Lemay parameters. X ux plus lambda dy y sigma y. So you see all of these look slightly similar to each other. Only the subscripts are different. dy uy plus lambda dx ux sigma x y equals mu derivative of the space u plus so this is x, this is y of x. So I hope they are more overcomable in this form than what I had last time. And to summarize, we have density is only dependent on space. We have lambda is also just dependent on space. Mu is mu x, and mu I is dependent on both space and time, and the same with the stresses. J sigma ij x t. Like so. So these are the same equations as for project alpha, if I remember correctly. And then we have the boundary conditions, which is the normal n. So there's nothing escaping this, well, area big sigma, which is 0. And initial condition is it should be quiet. Zero equals 0. Does that look overcomable? So, as to say, we did with the 1D acoustic. So here we are introducing two more elements of complexity, we are increasing the dimensions and also using a more advanced equation. So instead of the acoustic equation, we're using the elastic, which introduces more effects in the Earth. So this is more physically correct for using for simulating waves in solid media. But we are going to use this to create a spectral element solver for it. So then we creating weak formulation by introducing a test function and integrating over space. So C is the test function here. C is partial derivative of the xy stress C plus D. And then we integrate this over space. Again, we'll do an integration by parts, where we'll see that we can zero some of the terms. X minus x dx. Just correct this. That's right. Plus xy c d no dy this time minus dy c d omega plus x c d omega, like so. And now we can use the boundary conditions. So you see here we should have nothing escaping. So this is 0. So this is a split repetition from last time. And the same in the dy direction. It's also 0. Which is similar to what we had for the acoustic equation. And also in the exercise with the diffusion equation. We do this partial integration by parts, and we see the equation becomes, well, a bit easier to handle. Good. And then if we can write this up, so if you could use more space down here. See that we get so do you understand this d sigma and the dx dy? I mean, instead of writing this, some of you might have written dx dy instead of this. It's just that you integrate over the whole space. So instead of writing dx dy, you can write d sigma because that is your element. You can either have it in both the x and the y direction, so you, well, that was a bad explanation. So let's see. This is sigma. So d sigma will then just be a small part of it. And since we have x and y, like so, then we can also say that we have a small dx here and a small d there, and this is a square, so this is the same. So if you look quist, it's just a notation thing. Anyway, so this is what we had over there, and then we have these two terms here, which you take over to the left side and sum them. So that's sigma xx psi plus sigma xy dy c and we need a parenthesis for this, and this should be equal to the force term we have over here. C the sigma, like so. And then I should stand to reason that we can do something similar with the rest of the terms. So this is only the first term, and we have 4 more. But I won't go through them in detail because that's just a lot of writing. So you can see if you just substitute the x with the y's and the y's with the x, then we have the solution for the second equation for the y stress, no, the y displacement. But I need more space to write them up. So let me just repeat the one down there so that we have everything collected. Psi d sigma x dx psi plus sigma y dy c over space again. And force term as well. Dx. First equation. Second one. Y. D sigma plus sigma y dy c sigma x y dx c over space y c d sorry d omega, like so. And then just skipping a bit, then we can also have the stresses. So we can do the same trick with the test function and integrate over space, and do the partial integration. And then we get the following equations or weak formulations for the stresses. Then we have again, oops, x mu x ux psi plus lambda dy y c of the sigma. And then we have 2 more. Sigma y c over space sigma lambda plus 2 mu. Again, we can just, instead of dx ux, there's dy c lambda. Dx psi. Yep. So you see they look pretty similar, only the indices are switched. And then we have the odd one out, which is the xy stress. Xy. Mu x y mu x c t sigma. Like so. So this is just a lot of legwork to get a weak formulation of the elastic wave equation. I mean, you can write it more compact if you start to use indices, but that's just going to be confusing at this point in time. So then we have the weak formulation. Next is to discretize it. So then I will just list up some conventions we are going to use. Yep. See, this should be fairly evident. X is J y plus 1 is a vector. Then we have the Galerkin projections. So UP. So the P here can be either X or Y, just to save some time or space. T. Then we do the same thing. We have a basis for it. J T J, but now we need two basis functions. So this is actually a double sum. It's here. Maybe we should just write this as a double sum as well. So, because you have to sum the basis functions in both x direction and in y direction to make sense of this. This P is either x or y, just to save some space. And similar for the stresses, we have Galerkin projections for them as well. So P, Q. Yes.
Why we have to test this function?
Test the function.
Why we have to?
Oh, sorry. This should be an equal sign. Yep. P, Q. So I guess you get the ID now. Again, double sum. 1 J equals 1. This 1 equals 1. Oops. Sigma P Q and J. Sigma IJ of X, where P and Q are X and Y. So then I think we have all the projections we need for this. And then we can use these projections or approximations, or what you want to call them, into the weak formulation. And then we're cooking. Let's see. I'm just going to go over the equations today. And then again, we get integrals we need to evaluate. So, in a similar fashion, so this is mostly a repetition of the 1D. Get that the so this is the element-wise. So now we have discretized our big element into smaller elements, and I'll show an example of how these sigma e's can look like later. Psi CKL, I said. Sigma, I took away the bottom. This is the integral we want to evaluate, and similarly, we are going to have a double sum. I plus 1, plus 1, j plus 1, plus 1. J, C, J, I, J, C, K, L, D, sigma. Yes. And this again will hold for all the elements. And again, we need to have a reference element. This time we will use a 2D reference element. Again, we'll call it lambda, but it will look kind of different. So we want to go from this element here into a element here. And this lambda has to be a two-dimensional element. Minus 1 to 1, x minus 1. 1. So this is our, let's see, we can say that it's something like this. This is our sigma E. And the lambda will be more regular. We introduce a, let's see, let's go from sigma to the transform Fe, and the inverse transform Fe inverse. I could probably do this over here. No. So, Fe goes from lambda, so this is going this way into sigma E, and the inverse goes from lambda E to the lambda. So this we have the excess living, such that it's transpose size over here, size there. So this is fairly similar to what we had in the one-dimensional case again, especially when you abstract it with just functions. But we also need to think of how this scales. So if you remember the Jacobian from I think this is math 2 or something, so calculus 2. Then we need to have the derivatives in order to scale this correctly. So this is fairly similar to what we did in 1D again, but this is a more generalization of the concepts of the change of variables. So again, this is what we want to solve, but we have to do some legwork to get there. So I'm going to introduce a arbitrary function g, and then try to do a change of variables. So this f in my note, but I'll try to have g instead. So this is an arbitrary function, arbitrary 2D function. Dx dy. So this is nothing mysterious, this is just notation again, because this is 2D element and we can integrate over x and y instead. Then, so this is in omega, and if we have it in lambda, we will have g of, well, x is going to be a function of, oops, c1, 2, so that's where we've transformed the x coordinate, and we also need to transform the y coordinate. So these are the first and second components in lambda space. And then we use the Jacobian, which I'll come back to. C1, C2, the C1, C2. So now we've done a change of variables. Now we've kind of scaled this space, or stretched or squished this space omega into the space, the regular space, big lambda. Which is to say, we've taken this trapezoidal element and made it into a square. And a shorthand notation for this would be instead g big lambda. So this is basically the same, but just in a vectorized notation. And then there's j here. This is the determinant of the matrix dx xi x2 dy x1 dy x2. So this is basically just a scaling factor. How much have we stretched or squished this sigma? No, sigma. I said omega element. That's called the Jacobian. You've done similar stuff in calculus too, so. Am I missing a page? Nope. So then we can come back to this again. It's going to need more space. So if we then apply this general transformation to our first integral, we have 5 of these, but we're not going to do all 5. Then we get, again, double sum j equals 1 plus 1 rho of x psi u x ij, and only of time. Then we need a transform of our test functions or basis functions of xi kl I like so, and then j the lambda. Yes. It looks complicated. And then, again, these are basis functions, and we're going to use Lagrange polynomials. So, this Cij of x xi c j of just lambda of xi is li of 1 and xi 2. So, no, should be a j here. So you said that it's just the product of something going in the, or a polynomial in the xi1 direction and a different polynomial in the xi2 direction. What is xi1 and xi2 direction? Well, xi1 direction is this. Oops. xi1 and xi2 is just up. So instead of x and y, we've just, well, instead of introducing more symbols, we just said xi1 and xi2. And we're getting there. And again, we use this GLL quadrature. Am I going a bit too fast? Do you want time to write off the blackboard? Oh. So yes. Questions? Did you get the idea with the xi1 and xi2? It's just x and y transformed in the basis elements. X and y, like so. But then we're still on this, and we will apply the GLL quadrature again. Oops. again only for one element. X, T, K, L, T sigma, so it's the same as we have on the left-hand side there. We are now up to 4 sums. I plus 1, plus 1, I, because we are also solving the integral in 2 dimensions. Plus 1, and then is it n or n or n? It's m equals 1 and n equals 1. So these 2 extra because of the GLL quadrature. And then some weights. Wm, Wn, rho, bar, sigma, N, x, I, j, t, I, sigma 1, m, l, j of xi to n, l, k, sigma xi1, and l, xi 2, n, and then Jacobian. Sigma mn. Well, this can be made vastly easier because we have again the expression that for L I of xi k is the delta function by k. So you see that a lot of these basis functions are going to disappear. And we end up with just the weights, which are pre-computed. Rho bar, oops. KL, as well. U, X, KL, T, and then just the Jacobian. KL. So KL is 1K and sine 2 because 2 dimensions. And then this again is similar for the y, uy term. And since the reason, we can also do this for the stresses. But I think we should do that after a 15-minute break. And then I'll have time to actually show an example of how this is implemented by a colleague of mine. Any questions? Nope. I'll try to summarize these a bit neater.